Okay, I want to take a moment and show you this PhET website that's put out by University of Colorado Boulder, and they have a lot of great simulations in math and science. If we click on simulations, it brings up a pull-down menu, we choose physics. Within the study of physics, there's all these subcategories. I think we want to focus on motion for this course, and if we scroll down through the 32 results, somewhere in here should be projectile motion simulation. We could just as well go here and type in projectile motion if we know what we're looking for. So either way, we're going to get there and hit download. It downloads quickly because it's not a very big file. And here's what it looks like. So we get a chance to investigate projectiles launched at any angle. So we launch our projectiles from this cannon, and you can also adjust the initial height. So to keep it simple, let's stick to projectiles launched across level ground and bring the height down to 0. We can also adjust the speed with which the objects come out of the barrel of the cannon. And the goal is to hit this target. So we're going to have to use the equations that we've derived in the previous video lesson. Not sure what the statue of David is doing here, but that's fun, huh? So let's make the angle 30 degrees and keep the speed at 15 meters per second. So grab a calculator, and using the formula, range is equal to v squared sine 2 theta over g. We should be able to work this out to make a prediction. So if the angle is 30 degrees, double that would be 60. We take the sine of 60, multiply it by 15 squared, and divide that result by 9.8. Gives us a predicted range of about 19.9 meters. So let's slide our target and see if we were right. So we hit the launch button, and sure enough, bullseye. If we wanted to make it more realistic, we can click on air resistance, and now when we launch it, it doesn't land quite so far away. But then that wouldn't be a study in free fall, right? Free fall is the motion that results when the only force acting is gravity. So we'll save this for a future chapter and leave the air resistance out. So let's erase both of those launches and try again. So our 30 degrees hits in the target. You learned that any two projectiles launched at complementary angles should share the same range. So when we fire at 60 degrees and keep the speed the same, again, we find the exact same range. So I don't want to steal your thunder and show you all the possibilities of complementary angles. I encourage you to download this simulation and try it yourself. But before I wrap this up, let me show you a couple more neat things. If we click on velocity vector components and choose slow motion, now when we launch it, we'll see that the horizontal component of velocity remains constant, and the vertical velocity starts out large, pointing upward, and gradually becomes less and less, reaches 0 at the maximum height. Well, why am I saying it? I should show you. There you go. You see the vertical component of velocity is the only one affected by the force of gravity. And you have other options. You can show the total velocity vector. You can show the acceleration vectors. So I think it would be worth your time to go to the PhET website and download and play with this simulation if you want to reinforce the concepts that were pointed out in the previous video lessons.